Hi and welcome to another video, and today we will be discussing the 2D Poisson equation. Um, in the last video lesson we discussed the Laplace equation in two dimensions, and we implemented a method to check the residual level for the pressure for the Laplace equation, and we implemented some boundary conditions for Dirichlet or fixed type boundary conditions and zero gradient boundary conditions. So today we will be discussing the Poisson's equation, and it has a lot of similarities to the Laplace equation, but it has got a source term on the right hand side, which is denoted by the letter B. So the equation states that dou squared p by dou x squared plus dou squared p by dou y squared is equal to B, and our aim is to implement this equation and converge to some residual level and break out from the loop when we reach that residual level. Okay, so here we are, and the discretization is similar to the Laplace equation, except that now we have got the Bing term, which is multiplied by dx square and dy square because it's on the right hand side. Okay, so all we need to do is implement this source term, and for this particular tutorial we'll be using the source term as two singular points of -100 and +100 at x equal -1/4. So this is a discrete location, so x 1/4 and y 1/4, and +100 at x 3/4 and y 3/4. So let's go ahead and do that. Let's go to our coding, and I still have got the Laplace equation that we did in the last video. So all we need to do is create a field which will be representing this source term. So let's go ahead and create a field. So we will say that this will be a fields class 2-dimensional, what was it called, vector field 2D, and this we will call it as B, and we will initialize it to the size of u, so u dot size, and on the column side we have a vector of fields of u0 size. Right, let's close the brackets, and there we go. I think we have got the B correctly now. For the time being, let's decrease the time step to something like 2, because we want to visualize this B field before we go ahead with the iteration. So let's say that for int I equal to 0, so I is less than B dot size I plus plus, right? Okay, and copy this, change to J, paste in twice now. Okay, so let's change to J for int J equals to B0 size J plus plus. So we said that x, we want +100 if x is equal to 1/4 and y is equal to 1/4, and -100 if x is equal to 3/4 and y is equal to 3/4. Okay, so let's go ahead and do that. basically if because we haven't passed the grid information yet, so we can take so one way is to use this for loop and pass the grid information, get the grid information from u velocity. But I just realized we could do it because it's just one single point that we need in the b source term. So what we could do is just say that int first location is equal to so total points in the grid, so n rows, which is described here, n rows multiplied by or divide by 4, and second location is at 3 by 4, and since we have x length and y length to be the same value, we don't need to do anything else. Just divide this by multiplied by 3 and divide by 4, and let's check out if these locations are correct. So first lock and second lock and end the line, so it should give us the correct value there. So the first one should be 20 divided by 4, which is 5. That's okay, but the second value is giving us an odd number, so let's check what is happening. N rows multiplied by 3 divided by, okay, so let's give some space here because it's not clear what is happening exactly between here. So, and we will put a comma in between and change this to one way we could do is just change this to a double to get the multiplication correct, and then also this one to double, then we can check. Five and 15. Okay, so it's correct now, but to change, because in indexing we use integers, not doubles, so we could just say that int first lock 1 equal to first lock, so this way it will convert the double to an integer, because we can't use doubles in indexing. So now all we need to do is just say that first lock 1 and first lock 1 at that point, so basically at 20 divided by 4, which is 5 by 5, so 5 and 5 here will be equal to, let's check our, is it plus? So okay, it's minus there, so minus 100, and b second lock 1 and second lock 1 is equal to plus 100, so two source terms. And to check if everything went okay, let's print this vector. So field of dot print 2d vec and print the b, and let's go ahead and compile and run. There is some error saying that alright, because we should change the value actually, not anything else, because this is still a two-dimensional vector field and the value is what we are interested in. So let's build and run the project. Okay, so we've got a minus 100 here and a plus 100 here, so this is exactly what we wanted. Right, so we got the source term modified and implemented. Now what we need to do is write this Poisson's equation, and this time what we will be doing is just adding a special kind of. Now we could just use the same equation and just say that minus so minus b minus, let's create a new double that will be equal to the mesh to, let's say, dx square double dx square is equal to mesh 2d dot dx multiplied by itself, and double dy square will be mesh 2d dot dy multiplied by itself, dy, and double dx square dy square is equal to dx square multiplied by dy square. And also we've got the denominator term, which is 2dx square plus dy square. So let's do that. Double deno equal to 2.0 times dx square plus dy square. And let's look again. So we are separating this term and we've got everything that we need. So here now what we need to do is dx square dy square multiplied by b, and here we should divide this term by, so let's actually combine that. So let's combine the denominator and double combined equal dx square dy square divided by denominator. Okay, so all we need to do now is multiply combined with b, and that's our Poisson's equation. So let's solve and build the project. And let's run it, build and run. Let's go to that directory where the folders coding, code light, build debug and bin, and this is our Poisson equation. Oh, we have only run for one iteration, so let's go back and change it to something like 1000 equations maybe. Let's build and run. We could run from here as well. Okay, so it's going, and you can see the residual levels falling already. If you press Ctrl C, it will resume. Unfortunately, it's actually closed. So let's run from here. I wanted to show you the convergence. So let's delete this. Also, let's change the file name to 2DPoisson. Again, let's rebuild. And navigate to the directory and run from here. This time we will wait until it's done. Okay, in 1200 iterations, it's only dropped to 0.01 power level. Nevertheless, we know that the residual is dropping, and we have implemented now the 2DPoisson's equation. So the next lesson is probably the most important lesson in this course, because We will be combining everything that we have learned together to solve for the two-dimensional Laplace equation in which, sorry, not the two-dimensional Laplace, two-dimensional lid-driven cavity in which we will combine the Poisson's equation and the momentum equations to get the full set of Navier-Stokes equations, and we'll be visualizing our results to make sure everything is okay.